getting set up, I will introduce them. So it's my pleasure to introduce Aws Albarghouthi from University of Wisconsin-Madison, and he always gives very, entertaining and, at least in my opinion, really great talks, and he's gonna tell us about In Search of the Abstract. And before we get started, I wanted to tell you a little anecdote with the two of us involving Ken, since I was encouraging everyone else to share their anecdotes. So let's see if Ken remembers this. So, Oz, do you remember this? Well, let's see. So Oz was visiting me when I was at Microsoft Research Cambridge. He was visiting me for a week, and we were working on something called multi-abduction, and we tried for like a day or two, working really hard, trying to come up with some algorithm that had termination and optimality guarantees for something. I don't remember all the details, but we were banging our heads against the wall, and we didn't manage to come up with anything we were satisfied with. So we decided to consult Oracle. So I wrote an email to Ken, and what, like 3 hours later or something, comes back a response. And then it said, well, you can't find an algorithm because one is not always guaranteed to exist. Here's a counterexample. Both of us felt pretty stupid at that point, but I think probably, as everyone knows, Ken is always like more than 3 steps ahead of you. So, that's my one Ken anecdote.
We still got to publish those. Somehow.
It will be a conflict with him.
Right. Only one person knows that it's wrong.
No, that was the one we submitted.
Yeah. All right, yeah. Well, thanks. It's an honor to be here. When Ranjit and Shul invited me, I just couldn't say no. Summer in Croatia. So who would say no to that? No, I'm here to honor Ken and his contributions and the intellectual impact it has had on my career, both as a graduate student and later on as a professor. So let's start about 90 years ago, and it's true, it's still not working. Worked yesterday. It's all right, whatever. So 1935, there's a French art journal called Cahiers d'Art, if I pronounce it correctly, and they had a conversation with Pablo Picasso, and you can read the conversation. It's funny because it's not really a conversation, and with normal conversation, there's an interviewer who asks questions, but this is just like one long rant, many pages by Pablo Picasso, and it's very quotable though. And one thing he says somewhere in the middle is, there is no abstract art. You must always start with something. Afterward, you can remove all traces of reality. And when you think about it, it makes sense that Pablo Picasso thinks this way, because if you look at his own career, he didn't start by painting what we consider abstract art. He started by painting sort of run-of-the-mill paintings of things you see every day and trying to capture them in their full detail, with the lighting, with the colors, with the feelings, etc. Right? But then something happened in the year about 1910 or so, where he started removing all traces of reality to end up with what we consider abstract art. This is supposed to be a guitar player. This is a painter and his model. And then this is probably a lot of people have seen Don Quixote. So as you can see, he started by capturing things in full detail and started removing stuff until he captured, objects with their just very essence, with the simplest possible way you can convey that object or a scene or a feeling or a person. And if you think about it, Ken's career has had a similar trajectory. His early work on symbolic model checking tried to capture systems in their full fidelity, right? Like you want to look at every single state in 10 to the 20 states and beyond, right? You don't want to leave any state behind, right? So this was kind of the first, I would say decade or so. And then the new millennium arrived and something happened. I don't know what it is, but he started to remove things. Yeah, so he got into his abstract era, and started removing things until, no traces of reality were left. Only thing was left is what we call now interpolants, right? And if you think about what interpolants are, they're kind of the equivalent or the analog of Picasso's, geometric shapes and lines and colors. They just, the minimal thing that you need to convey a scene or an object or a feeling, right? So this is the kind of the analog I see between these two careers, but there's one big difference. What's the big difference? The big difference is that if you look at Picasso's early work, it looks like, a run-of-the-mill painting that you can find at a thrift store. But if you look at Ken McMillan's early work, it is foundational in the field, right? Like symbolic model checking has become almost folklore in computer science, that it appears in other areas and they don't even cite Ken. And that's a great compliment. So it appears in like exact probabilistic inference. You can define a big probability distribution as a BDD with some numbers at the bottom, and you can push it through a system. You can do quantum simulation where you describe a gigantic quantum state as, again, a BDD with some numbers at the bottom, and you push it through a system and so on. Okay? So this idea of, or this sort of Picasso-Macmillan philosophy of removing things until no reality is left, not only shows up in sort of Ken's algorithmic research, but it also shows up in his writing and exposition and talks, as Andreas, for example, told us, and David in the morning also commented. And this kind of view has both influenced me as a researcher as well as in my own writing. So as a writer has also influenced me a lot. Starting from grad school and all the way until now, when I work with my students on topics that seemingly have nothing to do with Ken, but somehow Ken's influence remains. So I'll tell you my story with Ken's work. So it started in graduate school. I was at the University of Toronto, and I was a student of model checking and software verification. So naturally, I was reading Ken's papers on symbolic model checking, on Petri nets, on interpolation. Interpolation had just kind of become an area of study. And at the time, I hadn't met Ken yet. So for me, he was just like this mysterious researcher, right? And if you went to his website at the time, he didn't have a photo in his website. It was like this bare bones HTML. I think it said, "Hi, my name is Ken. Here's a link to Cadence SMV," or maybe a license or something like that. I don't know what it was. So for me, it was like this mysterious guy. And in 2009, Ed Clark visited the University of Toronto and gave a colloquium distinguished lecture on the history of model checking. And in the slide on symbolic model checking, he had a picture of Ken. I managed to find it on the CMU website. And I was like, oh, finally, I know what Ken looks like. And then I was sitting next to a senior student who had met Ken. And she leans over and she's like, "This is an old photo. It doesn't look like this at all." I was like, oh, it's an old photo. So, I did the math. I was like, well, his hair is probably gray now. And his beard is probably longer. I mean, he's a wise guy. So he probably looks like this at this point. So for me, the picture of Ken at the beginning was like of this wizard-like verification guy who writes these incredible papers, that I get to read as a graduate student. And then finally, I went to CAV 2010 in Edinburgh, and I finally met Ken. And to my astonishment, the guy ages backwards. So that was yeah. So this was how I was introduced to Ken and his work. And one of the first papers I read, which I think that's the same paper you talked about, is that right? Yeah. So this was assigned reading in Azadeh Farzan's class on concurrency verification, and it's about Petri nets. And I never used Petri nets in my own research, and I don't think I ever will. But this paper kind of stuck with me, not its technical details, but just how beautifully it's written, right? And David commented on that. I'm going to dig into it a little bit. So the algorithm is described in plain English, right? It's not like an algorithm environment in LaTeX or anything like that. Just described in plain English. So let's go through it. This is how it starts. Unfolding a Petri net is a game that can easily be played on a piece of paper. Wow, what a breath of fresh air. Though it quickly becomes tedious. First, place some initial tokens on your Petri net. For each of these tokens, make a copy of the place on which it resides in the occurrence net, and then label the copies appropriately. How nice, it's kind of like when you read a recipe and it says salt to taste, like, just label it appropriately. And what I like about it is that kind of like it doesn't insult the intelligence of the reader. Like the reader should know how to label. Like I shouldn't like just tell them everything, And then it says, now repeat the following process forever. And this is the process. Again, it's written in plain English. And one of the, if you look at the first line, it says, choose a transition. It doesn't tell you which transition to choose, just choose one, doesn't matter. And then at the end, it says, well, if you make your choices fairly and have infinite time, you will build the unfolding of your future. And when I read that algorithm, I was like, wow, you can actually write papers like this, right? And because, at the time, 2009, 2010, when I was looking at CAV papers, it looked like this, right? These were algorithms, right? And these are my papers, by the way, so I'm not trashing anyone. So when I saw that, I was like, wow, you can describe things so clearly. And that has stuck with me a lot. Another paper that I spent a lot of time reading from Ken is the lazy abstraction with interpolance, which Andreas doesn't like. He described second. What's that?
The second half.
Right. So the first thing that struck me about this paper is that the abstract is 2 sentences. That's the like if you submit something like this these days, it gets desk rejected. Like no abstract, desk rejected. Yeah. So the first sentence just says what he did. It's a new algorithm. The second sentence it says it does better than BLAST, which is great. And that's it. Like that's the whole abstract. But what's interesting about it is that if you look at the algorithm, again, the algorithm is just 3 operations: expand, refine, and cover. And if you apply these operations in whatever order, you might get a proof, you might get a counterexample, or you may just not terminate, right? So that's just the kind of the minimal amount of information that you need to construct an algorithm, or maybe a family of algorithms out of these 3 operations. So it doesn't dictate how you should order them, but it gives you the ingredients, and you're smart enough, go apply it in different ways. So these are kind of have had a lot of influence on my both research and writing, which is whenever I start with whatever I think I have a solution to a problem, I start with that solution, write it down, and then I keep removing things until I find a core set of operations that solve that problem or can be combined in a way that solves the problem. And I kind of put it in a rule of thumb advice to my students, which is if you it forces you to simplify your ideas a lot. All right, so recently my group has been working on quantum computing, and I'll just tell you a little bit about that work and how some of Ken's ideas are still kind of looming large. All right, oops. So traditional bits are 0 or 1. That's how we build computers. So it's 0 or 1. You can flip a bit or negate it, if you will, and if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. Qubits or quantum bits are the same thing. You can be a 0, and if you flip this bit, you become a 1. But as you can see, there's sort of a weight associated. So you can take this weight and divide it into two bits. This is called superposition. You're both a 0 and a 1 with some weight, or what they call an amplitude. And you can take also this amplitude and negate it. So you can have some bits or qubits with negative amplitudes. And if you take a qubit that looks like this and you negate it or flip it, the amplitudes of 0 and 1 swap. Okay? So it's kind of just very much like a normal computer. And the problem with quantum computing is that if you have 2 qubits or n qubits, you need 2 to the n different amplitudes. So even simulating this on a normal computer gets really challenging because you have to somehow represent 2 to the n different amplitudes. So there's this notion of stabilizers. So a stabilizer is a function that if you apply to the state, you get the same state back. Okay, so for example, if I take this state and I flip it, this is like a logical knot or an X in quantum computing called X. And if I flip the state, if I flip the amplitudes of 0 and 1, swap them, I will simply get the same state back. So I say that this function or this operator is a stabilizer for this state. It's a very, very simple concept. But it turns out that, you know, in 1997, Daniel Gutzman in his PhD thesis discovered that for some class of quantum states and quantum programs called Clifford states or Clifford circuits, we can represent the state precisely with n stabilizers. Okay? So you don't need the 2 to the n explosion. You can just find these n operators and describe the state. So the state will look something like this. Each of these is a stabilizer. So each stabilizer takes the state and returns the same state back. Okay? And then if you apply operations to this state, it simply updates each stabilizer syntactically to a new stabilizer. So what does this look like? Ranjit, you're saying something. Fixed point? Looks like predicate abstraction, I think. That's what I'm trying to say. Each of these is a predicate, right? And you find a fixed set of predicates, n of them, and you say, I'm going to use it to, you know, represent my state. And then every time you make a transition, you update, you get a new set of predicates. Some of them perhaps change, get negated, whatever it is. So when we saw this, we're like, oh my God, you know, it's predicate abstraction, and but it was so hidden so deep. Like if you look at the text on stabilizer and quantum error correction, it comes in from quantum error correction. You know, you'll notice that there's group theory, there's information theory, there is all the linear algebra, but you know, you start peeling, you follow the Picasso McMillan style of just removing to see what's down there. So you see group theory, you remove it, you see linear algebra, you remove it, and then ultimately you see predicate abstraction. And once you see predicate abstraction, what do? You can take your quantum circuit, you can represent it as a Boolean program, because it's predicate abstraction, and you can give it your favorite verifier, whether it's, you know, CBMC or CPA checker or whatever it is, and you can ask questions about it. You can ask reachability questions, like, is this state reachable with some probability? Are these two qubits entangled? And so on and so forth. So what's next? You know, quantum lazy abstraction, that's a natural next step. Quantum interpolance, maybe. And maybe there are some other things. So it's early work, but I thought I would share it. And with that, thank you, Ken, for all the art. Keep it coming. Oh, the questions.
So there's a lot of talk about quantum supremacy.
Yeah.
And what are the problems quantum computing can solve, but
Right.
cannot be solved on classical computers.
Uh-huh.
Except that this community has been able to solve problems classically.
You mean the verification community?
Mhm.
The verification community.
Formal method.
Yeah.
More broadly, the
Right. Yeah.
verification, SAT, CP.
Uh-huh.
We're solving problems that were considered to be, you know, beyond the reach, right?
Uh-huh. Yeah.
So now that you're talking about, if you go back to the slide,
Yeah.
you can apply this. You know, can we look at some of these problems that people say, no, cannot be solved classically,
Mhm.
and maybe we can.
It is conceivable. So one of the issues with this stabilizer formalism is the class of circuits we look at can be polynomially simulated in polynomial time on a classical computer. You can basically, this is the gate that's problematic. There are ways to kind of manage this exponential explosion, but ultimately you'll hit it. But for a class of circuits, the Clifford circuits, they show up in fault-tolerant computing. So at least we can ask, you know, verification questions about those circuits because they're going to end up in fault-tolerant computers if the physicists manage to build them. So, but yeah, so yes to both, I guess, questions. Yeah.
Yeah, maybe your answer kind of answered my question, which
Okay.
is that Clifford states, it seems like a very special.
Right, yeah.
And so
Yeah.
there has to be, for general quantum states, there has to
Right.
be a blow up somewhere.
You have to pay at some point,
Yeah.
there's no free
Now,
lunch.
is there a kind of representation theorem that says that you can represent any general quantum state as possibly exponential combination? Clifford state.
Yeah, exactly. So as I said, there's this gate, that's the problematic one, which is not a Clifford gate. And what happens is that you can remove it and replace it with a gadget called the magic state. And then you can take your circuit and represent it by exponentially many circuits that you combine the results at the end. And there are ways to manage that explosion. So maybe that's one way where you can do it lazily, for example.
Yeah.
But that's still, this is kind of recent results from recent months. So yeah. Other questions? All right. I'm not an art historian, by the way, so don't quote any of this. Cool. Thank you.
Thank you.